So part two of your KIN 225 class today, I'm going to be talking about a continuation of the steps that are involved in muscle contraction. Specifically, I'm going to be talking about conduction of the action potential from the axon to the muscle fiber. So when you activate a neuron by recruiting a neuron from your brain centers, you send an electrical signal through the neuron and through its axon, which is an extension of the neuron, to the muscle fiber, and then that's going to cause the muscle fiber to contract. So, I've showed this video before. I'm going to show it briefly again here. You have this action potential, which is like an electrical signal. That originally comes from the neuron that's connected to the muscle fiber, and it gets conducted down the muscle fiber membrane, then goes down that T-tubule, and that T-tubule is associated with the sarcoplasmic reticulum, which then releases calcium. So here you'll see calcium being released. And then that calcium, as you know, binds with troponin, and that causes tropomyosin to lift off of the actin, and then that allows the myosin to bind with actin and allows muscle contraction to occur. So what I want to go over here in more detail is what happens up here between the neuron and the muscle fiber membrane. So you have this electrical signal that's generated at the muscle fiber membrane. It goes down this T-tubule, and then that allows, that results in the sarcoplasmic reticulum releasing calcium, and then you get muscle contraction. What I want to cover now is what happens between the axon and the muscle fiber membrane to initiate that electrical signal that's generated at the muscle fiber membrane. So it all happens with this neurotransmitter called acetylcholine, and then an exchange of ions across the muscle fiber membrane that generates this electrical signal. So these neurotransmitters are called acetylcholine. That acetylcholine acts as a signal between the axon of the motor neuron. So this comes from a neuron that's located in the spinal cord. The acetylcholine acts as a messenger from the axon to the muscle fiber membrane. So the axon isn't actually attached to the muscle fiber membrane. There's a space there, and that space is called the synaptic cleft. So what happens with these electrical signals? So you get this electrical signal called an action potential that comes down the axon from the neuron. That causes calcium to enter that axon, and that results in activation of these acetylcholine vesicles. So this acetylcholine, again, is called a neurotransmitter. It acts as the signal from the axon to the muscle fiber to tell the muscle fiber to contract. So you get the action potential coming down the axon, causes calcium to enter the axon, and that causes these acetylcholine vesicles to merge with the axonal membrane. You get release of the acetylcholine into that synaptic cleft. You get binding of the acetylcholine with receptors on the muscle membrane, and that results in opening of ion channels. And opening of these ion channels causes a change in the charge on the membrane, which causes this almost like a wave of electricity that goes down the muscle membrane. So what happens here is you get acetylcholine binding to the receptors. That opens up sodium channels. You get sodium rushing into the muscle fiber. Then those sodium channels close, and you get potassium, that's represented by K, that rushes out of the muscle fiber. So that causes a change in the electrical charge along the membrane, and that's what results in that electrical charge being transmitted down the membrane and then eventually down the T-tubule to the sarcoplasmic reticulum. So this is kind of a bit of a summary. Propagation of the action potential or that electrical charge from axon to muscle. You get the action potential opens calcium channels in the terminal of the axon. Calcium diffuses into the axon, and that stimulates the fusion of these vesicles that contain acetylcholine with the axonal membrane. This acetylcholine is like a messenger between the neuron and the muscle. The vesicles release acetylcholine into the synaptic cleft, so that's that space between the axon and the muscle fiber membrane. The acetylcholine binds with receptors on the muscle membrane, opening up channels that allow sodium to go in and potassium to go out of the muscle fiber. Now, a key step here is that you get sodium going in and potassium going out. So I always like to show this video about frog legs and table salt. So table salt is mainly sodium, and it shows what happens when you add table salt to a frog leg. So I'm just going to have to boot up my computer that's actually hooked up to the internet here and YouTube. I'll just take a second here. I just have to log on to my video. Here's your YouTube video here. So this serves as kind of a memory aid for what ion goes into the muscle and which one leaves. So recall that sodium goes into the muscle during contraction, and potassium goes outside. So when you can see what happens when you add table salt or sodium to these muscles or the frog legs. So the table salt or sodium goes from outside the frog legs through the muscle membrane, and it actually causes the frog legs to start to twitch or to contract. So you can see them twitching away there. So that twitching is caused by sodium going from outside the muscle membrane to inside the membrane and causing that action potential and contraction of the muscle.
We put this on YouTube, set it to some music.
So there you go. So I'm going to go over the charges along the muscle membrane and then what happens during contraction and relaxation. So at rest inside the muscle fiber, sodium is low compared to outside the muscle fiber, and potassium is high compared to outside. The membrane of the muscle fiber or muscle cell is more permeable to potassium, so potassium leaks out faster than sodium leaks in. And these are both positively charged ions. So based on this, do you think the inside of the muscle fiber would be negatively or positively charged compared to the outside? So you have a greater amount of sodium that's leaving and a lesser amount of, a greater amount of potassium that's leaving and a lesser amount of sodium that's leaking into the fiber. So because these are both positively charged, you have more positively charged ions leaving the muscle fiber. So your membrane ends up being negatively charged at rest. During contraction, sodium rushes into the muscle fiber, so that changes the charge on the membrane to positive. And that change to a positive charge is called muscle depolarization. And then you have potassium that leaves. When potassium leaves, it's called repolarization. And what actually happens is that too much potassium leaves so that your charge goes more negative than usual. So if you remember, the resting membrane charge is minus 70. In this case, following contraction, too much potassium leaks out and you actually go more negative than usual. And during that period, it makes it more difficult for the muscle to contract. So it makes it more difficult to get depolarization of the muscle. And what I'm going to do is I'm going to stop the video here, and in the third part of the video, I'm going to review what happens to the muscle membrane charge with depolarization, repolarization, with the exchange of sodium and potassium.